Hi everyone, welcome to our physics class. In the previous class, we have studied about Ampere's circuit law and its applications, derivation of expression for magnetic field inside a current carrying solenoid, and derivation of expression for magnetic field inside a current carrying toroid. This is moving charges and magnetism part 6. Okay, well, let's start today's class. So, the first topic is how does a current loop is behaves like a magnetic dipole. So, this topic is very important for 3 mark. Show that the current loop as a magnetic dipole. So, first here, let us consider a circular current loop. So one end of the loop is connected to the positive terminal of the battery and another end of the circular current loop that is connected to the negative terminal of the battery. One end of the circular loop is connected to positive terminal of the battery and another end is connected to the negative terminal of the battery. Current is always drawn from positive terminal. The current is flowing like this, that is in clockwise direction. So if the wire carrying current means that is surrounded by the magnetic field lines. So that can be determined by using right hand thumb rule, right? So here the wire is held in the right hand, thumb pointing in the direction of current. The fingers encircle, which gives direction of magnetic field lines around the current carrying wire. So here the magnetic field lines are in anti-clockwise direction because they are current flowing vertically upwards. So the direction of magnetic field lines around the current carrying wire is anti-clockwise direction. But here the current flowing vertically downwards. So again held the wire in right hand, thumb pointing in the direction of current, that is downwards. So the fingers encircle, which gives the direction of magnetic field line, right? So the direction of magnetic field lines here, that is in clockwise direction. So here the magnetic field lines are anti-clockwise. Here the magnetic field lines are clockwise. But at center, the magnetic field lines are almost straight. That means at the center of the loop, the magnetic field is uniform. So magnetic lines of force at the center of current loop are straight. It means that magnetic field at the center of the current loop is uniform. So this is the animation of the magnetic field lines around the current carrying loop. So actually the phase of the current loop, phase of the current loop in which the current flows clockwise direction. Phase of the current loop in which the current flows clockwise direction. That phase is just behaves like a south pole. So let us take a Bohr magnet. So north pole of Bohr magnet is moving towards this phase. So what happens means north pole of Bohr magnet will experiences attractive force. So that clearly shows the phase of this loop is just behaves like south pole. Or in other words, the south pole of Bohr magnet is moving towards the face of the loop. So south pole of Bohr magnet will experience a repulsive. So it confirms the phase of the loop in which the phase of the loop in which current flows clockwise. That phase is just behaves like a south pole. Okay. So the phase of the loop in which the current flows anti-clockwise direction, actually that phase is just behaves like a north pole. So let us take again a Bohr magnet. North pole of Bohr magnet is moving towards the face of this current loop. So what happens? The north pole of Bohr magnet will experiences the repulsive force. So or the south pole of Bohr magnet is moving towards the face of this current loop. So then what happens? The south pole of Bohr magnet so will experience attractive force. So that confirms the face of the current loop in which the phase of the loop in which current flows anti-clockwise direction. The phase of the loop in which the current flows anti-clockwise direction. That phase is just behaves like north pole. So actually each loop having two phases. Okay. So the phase of the loop in which current flows clockwise, that phase is just behaves like a south pole. So another phase, actually in another phase, the current flows in anti-clockwise direction. So the phase of the loop in which current flows anti-clockwise direction, that phase is just behaves like north pole. That means the has current loop has two poles. Current loop has two poles separated by a very small distance. Hence, the current loop is just behaves like a magnetic dipole. Okay. So, actually here, one phase of the loop behaves like south pole and another phase is behaves like north pole. So, current loop has two poles separated by a very small distance. Hence, the current loop just behaves like a magnetic dipole. So, here first, let us consider the mathematical expression for magnetic field at a point on the axis of the current loop. Magnetic field at a point, magnetic field at a point on the magnetic field at a point on axis of circular current loop. So what is the expression for magnetic field at a point on the axis of circular current loop? So that is B is equal to mu naught divided by 4 pi 2 pi n I or square divided by or square plus x square power 3 by 2. Okay. Suppose if x is much greater as compared to the radius, then x square is negligible. Not x square or square. Or square is negligible because r is very small, right? That is why r square this is negligible. Okay, now this expression becomes, what is the meaning of x? X is the distance from observation point to center of the circular current loop, or is the radius of circular current loop. X is much greater than or means the point on axial line, that is far away from the center of the circular current loop. So in that case, R square is very small, that is negligible. Now this expression becomes B is equal to mu naught divided by 4 pi to uh, pi R square. So pi R square, actually this is the area of circular loop, is it not? So N I into A. What is the meaning of A? A is the area of the circular current loop. So divided by, so here R square is negligible, x square power 3 by 2. So finally we will get B is equal to mu naught divided by 4 pi to M. M is the magnetic dipole moment of circular current loop. So here Q2 get cancels divided by X cube. So where M is equal to N I A. Actually N means number of turns. So here just one turn is there. Circular current loop having only one turn. So for circular current loop, circular current loop, what is the value of n? N is equal to 1. So that is why the magnetic dipole moment of circular current loop is I into A. So the product of current flowing through the circular current loop and area of the loop. Okay. So this is the magnetic dipole moment. So the direction of magnetic dipole moment, that is same as that of the direction of the normal. Normal is always perpendicular to the plane of the loop. Magnetic dipole moment of any current loop, magnetic dipole moment of any current loop, that is exactly equal to the product of current and its loop area of the loop, product of current and area of the loop. Okay, its direction is defined to be normal to the plane of the loop. So in the sense given by right hand thumb rule. Okay, so look at this loop. So here this is the direction. Normal is always perpendicular to the plane of the loop. Okay, so this is held in the right hand. So thumb pointing in the direction of magnetic dipole moment. So this is the normal and this is the direction of magnetic dipole moment. And the fingers encircle, which gives direction of current flowing through the circular current loop. So in this case here the magnetic dipole moment is vertically upwards. That is due to right hand thumb rule. Okay. So direction of normal, direction of magnetic dipole moment, both are same. Magnetic dipole moment. So this is a vector physical quantity. It is not a scalar. It is having a particular direction. Okay. So magnetic dipole moment is a vector physical quantity. So what is the SI unit of magnetic dipole moment? So that is also very important. So the SI unit of the magnetic dipole moment is ampere. Current is measured in terms of ampere. Area is measured in terms of meter square. Ampere meter square. So this is the SI unit of the magnetic dipole moment. Okay. So actually the electric intensity at a point on the axis. Okay, electric intensity, electric intensity at a point on axis of electric dipole. Electric dipole. Electric intensity at a point on the axial line of electric dipole. That is E is equal to, this is for short electric dipole. That means R is much greater than A. So in that case, we will get 1 divided by 4 pi epsilon naught. So 2P divided by R cube. What is the expression for electric intensity at a point in the axial line? E is equal to 1 divided by 4 pi epsilon naught 2P R divided by R square minus A square whole square, right? So if R is much greater than A, so then A square is negligible, right? Then electric intensity is 1 divided by 4 pi epsilon naught to PR divided by R per 4. So 1R get cancels. So finally we will get E is equal to 1 divided by 4 pi epsilon naught to P divided by R cube. So call this as equation number 1 and call this as equation number 2. So comparing this with the expression, okay, comparing this with the expression for electric intensity at a point on electric dipole. So actually here M is the magnetic analog of P. M is the magnetic analog of P. M is called the magnetic dipole moment. P is called the electric dipole moment. So comparing equations 1 and 2, we can conclude that. Okay. So from equations 1 and 2, we can conclude that M is magnetic, M is magnetic analog of P. M is called the magnetic dipole moment. P is called the electric dipole moment. Okay. So this clearly shows what current carrying circular loop. Okay. Circular current carrying loop is just behaves like a magnetic dipole. Okay, the next topic, a torque on a rectangular current loop placed in a uniform magnetic field. So a rectangular current carrying loop is placed in the presence of uniform magnetic field. Actually, it will experiences torque. So first here, let us consider a rectangular current carrying loop. This is a rectangular current carrying loop A, B, C, D, A. This is a rectangular current carrying loop. Okay. So actually here current flowing in the loop, that is in anti-clockwise direction, right? So if a current carrying conductor is placed in the presence of uniform magnetic field, it will experiences force, that is F is equal to Bill sine theta. Okay. So the current carrying conductor is placed in the presence of uniform magnetic field. It will experiences a force, that is F is equal to Bill sine theta. So in vector form, F vector is equal to I of L vector cross B vector. Okay. So the direction of force acting on a current carrying conductor that can be determined by using the Fleming's left hand rule. Okay, so actually here the side BC initially, so the L vector that is parallel to B vector, right? So AB is perpendicular to B vector, BC is parallel to B vector, and B vector means direction of magnetic. CD, so that is perpendicular to B vector, DA, that is parallel, anti-parallel to B vector. So if L vector, that means the length of the conductor is parallel or anti-parallel to the direction of magnetic field, so it doesn't experience any force. Actually here, the force acting on BC, force acting on DA is zero, because BC is parallel to direction of magnetic field. Let us consider a small element here, that is the DL vector. So our complete the length is L, that is L vector. So L vector is parallel to B vector. What is the angle in between them? That is zero. So F is equal to B sine zero. So sine zero is zero, zero and anything is zero. So the force acting on the side BC is zero, because here L vector is parallel to B vector. So here this is L vector. L vector is actually anti-parallel to the B vector. The angle between L vector and B vector is 180 degree. So sine 180 is also zero. So the force acting on the side BC is zero. The force acting on side DA is also zero. But the force acting on AB and CD, that is not equal to zero. Okay, actually that is maximum. So here this is the direction of L vector. Okay, so that is vertically downwards, and this is the direction of magnetic field. So here L vector is perpendicular to B vector, theta is 90. So the force acting on AB is maximum, because psi 90 is 1, right? Because here L vector, that is L vector is perpendicular to B vector. What is the angle between L vector and B vector? That is 90 degree. So the force acting on the side AB is maximum. So what is the direction? It is very important. So that can be determined by using Fleming's left hand rule. Stretch out the first three fingers of left hand. Stretch out the first three fingers of left hand in three mutually perpendicular directions. So look at this diagram. So stretch out the first three fingers of left hand in three mutually perpendicular directions. Four finger points in the direction of what? The magnetic field, right? So middle finger points in the direction of current flowing through the conductor. So here current flowing through the conductor, that is in vertically downward direction. This is four finger points in the direction of magnetic field, the middle finger points in the direction of current flowing through the conductor, thumb pointing in the direction of force acting on the current carrying conductor. So that is normally outwards, right? So this is the direction of force. Actually here AB will experience a force that is moving outwards, right? So in a similar way, so here the current flowing vertically upward direction, and this is the direction of magnetic field. Again, stretch out the first three fingers of left hand in three mutually perpendicular directions. So the four finger points in the direction of magnetic field. This is the direction of magnetic field, that is from left to right, and middle finger points in the direction of current flowing, that is vertically upwards, right? So thumb pointing in the direction of force acting on CD. So that is inwards. Okay. So here force acting on AB, that is normally outwards. The force acting on CD, that is normally inwards. Actually, the magnitude of the force acting on AB, magnitude of force acting on CD, both are same. That is BIL. Okay, but their directions are different. So unlike unlike, so parallel forces acting on a body produces the rotational motion. Actually, that is called the couple. Two equal, unlike parallel forces whose lines of action is different, that constitute a couple. What is the effect of couple on a body? That is produces the rotational motion. Okay, that is the effect of the couple on a body. If a couple acts on a body, so body will get rotated. The rotational ability of the couple, that is called the moment of couple. Actually, that is called torque. Okay. So now look at this animation. Actually, here, so this is a current carrying rectangular loop. So actually, one end of the loop is connected to positive terminal of the battery, and another end that is connected to negative terminal. So actually, current is flowing like this, right? Current is flowing, that is in anti-clockwise direction. Okay. So now here apply the Fleming's left hand rule. So this is the direction of current. This is the direction of magnetic field. So the force acting is vertically upwards. Okay. And then again apply the Fleming's left hand rule here. So this is the direction of current. This is the direction of magnetic field. So the force acting is vertically downwards here. But here the force acting is vertically upwards. Okay. So finally, a torque acting on a current carrying loop that is placed in the presence of uniform magnetic field. Okay. Now we have to calculate. So what amount of torque is acting on a current carrying rectangular loop that is placed in the presence of uniform magnetic field. Actually, here the force acting on the side BC, that is 0. Force acting on the side BA is also 0. And the force acting on the side AB, force acting on the side AB is maximum, that is BIL. What is the meaning of L? L is the length of the side AB. Okay, length of AB, length of CD, both are same. So Bill sine theta is the angle between L vector and B vector, so that is 90 degrees. So the force acting on the side AB is maximum. Okay, it consider simply that is F. F is equal to BIL, and call this equation number 1. And the force acting on the side CD, that is also same, right? So BIL. So here L vector is vertically upwards. Direction of L vector, direction of current, both are same. So L vector is vertically upwards. So B vector, that is from left to right. So angle in between them is 90. Sine 90, sine 90 is 1. Again, the force acting on CD is BIS. So that is also maximum. So call this equation number 2. So what is the direction of force acting on AB, direction of the force. So this is very important, that can be determined by using Fleming's left hand rule. So here the force, direction of force acting on AB, that is normally outwards. Okay, so here dot indicates the direction of the force acting on the side AB, that is normally outwards. But here the direction of force acting on CD, that is normally inwards. The cross mark shows the direction of force acting on side CD, so that is normally inwards. So here force acting on AB is normally outwards. So here force acting on CD is normally inwards. Two equal and opposite forces acting on a current carrying rectangular loop. Okay, so what is the meaning of torque or the moment of couple? Actually, here net force acting on the rectangular current carrying loop is zero. The net force is FAB minus FCB. So BIL minus BIL get cancels. The net force acting on current carrying loop, so that is zero. So the couple, moment of couple or torque, moment of couple or torque is equal to magnitude of one of the force, into the perpendicular distance between two forces. So the perpendicular distance between two forces, that can be calculated by using this diagram actually. So this is F1 vector. F1 vector is normally outwards. F1 vector means this is FAB vector. So this is FCD. This is normally inwards. This one is normally outwards. Okay. So let us consider this one as n cap. N cap is the unit vector, indicates the direction of magnetic dipole moment, direction of normal. Okay, so theta, that is the angle made by. This is angle theta, angle made by direction of normal and direction of magnetic field. The angle theta. So what about this? This angle. This one is 90 minus theta, right? So this one is also 90 minus theta, because these two are vertical opposite angles. This is theta. Okay, why? Because this is the angle 90 degree. So the sum of all angles in a triangle is equal to 180 degree. So that is why this value, that is exactly equal to theta. So and then actually here we have to find out the perpendicular distance between two forces. Let's consider this point as P, one as Q, one as R. Now look at this right angle triangle PQR. Okay, we have to calculate the perpendicular distance between two forces, right? So in the triangle PQR, what is the value of sine theta? Sine theta is equal to perpendicular divided by hypotenuse. Okay, perpendicular, that is RQ. The hypotenuse, actually this is the breadth of the coil. So let's consider here AD is this is the length. Okay, this is breadth coil. This one is the length of the rectangular coil. Okay. So PQ is B. B means breadth. Okay. So RQ is equal to B sine theta. So this is the perpendicular distance between two forces. So the magnitude of one of the force is BIL. So the perpendicular distance between two forces is B sine theta. Okay. So length into breadth, that is the area of the current loop. B I A into sine theta. So the product of current in the loop and area, what is that? That is the magnetic dipole moment, right? The direction of magnetic dipole moment, that is same as the direction of the normal. So what is the symbol of torque? Tau. So finally, we will get tau is equal to mb sine theta. So in vector form, in vector form, can be written as tau vector is equal to m vector cross b vector. Suppose if the coil has, suppose if the rectangular coil has n number of turns. So then the torque mathematical expression is n d I a sine theta. So this is tau is equal to n d sine theta. Okay. So here m value is n I a. Okay. So when the torque acting on the current loop is maximum and minimum. So that is also very important. If m vector is parallel to b vector, then theta is equal to 0 degree. Okay. Torque acting on current carrying loop is 0. If m vector is anti-parallel to b vector, so then theta is equal to 180 degree. So in that case also torque is 0. Okay. If this is first case, second one, last one. If m vector is perpendicular to b vector, then theta is equal to 90 degree. When torque acting on the current loop is maximum, that is mb or NIAB. For current loop, IAB. Okay. So this is also very important for 3 mark. Okay. Thank you.